Okay. All right, can you hear me? Good.
Yes, yes.
Thank you. Okay, so to continue with our lecture today, just to remind you, last time we were able to go from what we call a microstrip, which is a type of a integrated line. I mean, at least in the beginning of in microelectronics, it was used extensively. Now it's still used, but there are other types of lines, but it's a traditional line. They were able to take a number of steps and take this one and make it something that we have seen before, which is a parallel plate structure that is separated by one material that is covering only the area in between the two conductors. And we assume that these are the same ideal parallel plate conductors that we have seen when we calculated the capacitance. At the same time, because there is a current that flows, as we said, this one carries also an inductance. So it's a capacitive and an inductive line. But we have changed slightly the geometry of the width of the line. The long dimension is the dimension of propagation. So this is the long dimension, you will see that. So this is the width, W. The thickness remains the same, unchanged. We modify the width and we modify the electric constant of the material. And that allows us to go to this kind of structure, which is ideal. And from this structure to go to this one symbolically. So this structure, which is ideal, symbolically is represented by these two big wires and maintains its length. All right, the length of the line is maintained. And here, therefore, we take a three-dimensional line and we go down one dimension. All right, whenever you see thick wires, it implies that they have a dimension, only one, and is along the direction of along the direction of the current. And whenever you see thin lines, that implies we have no physical length involved. These are the traditional symbolic representations of circuits. So now, in transmission lines, we have a combination of structures with length with circuits. All right, and this is what we had in simple circuits. This is here. This is what we are going to have now in transmission lines. So now, what we are going to do today are two things. One, which I'm not going to derive here, but I'm going to ask you to derive as homework. This Sunday, the homework I'm going to give you. I'm going to ask you, the capacitance of a line like that, how to derive it, all right? The electrostatic capacitance, we know how to derive the electrostatic capacitance when we apply a voltage. We've done that. We also have derived inductances for loops, all right, for a single loop. And now what I would like you to do is to have, and in my notes also very briefly towards the end of the magnetostatics, we talked a bit about the inductance that flows in a structure like that when the current is going, as you can see here. This is in fact, let me add to this structure so you can see the dimension, the other dimension. You can see its length. So this structure like this up here is going to have that dimension remain. You remember we said that? This is the length of the line. And what you see here in detail on the front is the cross section. Therefore, this length dimension remains. And what happens when I show you here with the green, it implies that the current, which always flows in a structure like this, both the charges and the current will be in the lower surface of the upper conductor, upper surface of the lower conductor. All right, so as you can see here, these charges and these currents always are on the lower surface of the upper conductor and on the upper surface of the lower conductor. All right, so up here in green, you have a current that flows like this. And then below it, it comes out that way. Well, I'm not doing it very well. Let me use another color here. It comes out this way. The lower conductor. Now, for that, I will give you the structure, and I will ask you to derive the capacitance and to derive the inductance. We'll assume that this is W effective, so practically we have gone from the microstrip to the left. We have now moved all the way to this one. And for this structure that we have simplified, we now can find the capacitance and the inductance, but because the structure has a length, we define those per unit length. All right, so we take a particular length. You can take a length L, find a total inductance, a total capacitance, but to find the per unit length, you will have to divide both the capacitance and the inductance by this dimension. As a matter of fact, we use length here, and then I will write it so you don't mix it up with the inductance. So practically this is length. Let me do it here. I will put L sub B, where L sub B is length of line. All right, so we're not gonna see it anymore as, in that way, but I don't want you to mix up this one with the inductance L. All right, so I'm gonna write it like this explicitly. All right, now, and also I have it as lower L. As you can see here, I have it as lower L. Okay. Now, so as I said, the capacitance we have derived, the inductance we have briefly. I would like you in the homework to show me that these are the capacitance per unit length, inductance per unit length for this kind of geometry. That's going to be the individual homework. So now that I have, here is what we are moving on from here on. Now that I have both the capacitance and an inductance per unit length, I will assume the following. I will assume that I start with a line, a representation. Let me see. I will start with a transmission line and duplicate here. I will assume that this line is has a length. All right, so you would always make sure in your designs to show that the lines are thick. Otherwise, you're going to get totally mixed when you write things down. Then I will assume that here I excite it with a harmonic source. And this harmonic source for now in the time domain will be V naught, involves cosine omega t. Okay, so that's how I define it. And then I will assume that at the end, I have a simple resistive load for the time being. Okay, this is a bell. I will call this, and you should always do that, give it names to any place on the transmission line where you have the beginning, the end, and any place in between where you add anything. You will have to add points because these points now are important. The points, the port, we call it port A prime, input port. You're gonna hear me talking about this quite a bit. And output port, BB prime. And we will always call them like that because there are two. There are two distinctly different points, all right, physically separated. And this one is gonna have a length. Usually we're gonna indicate that. Let me see here as the Z direction. And you will put for now Z equals 0 here in the beginning of the line. All right. Now I will do the following. I will say, what if I can distribute, I know that per unit length, this line has an inductance and a capacitance, all right? However, what that means is the following. It means that if I separate this line into small sections, many small sections. So let's assume that I separate the line in small sections, and this is gonna be C, C prime, D, D prime, and so on, where each of these sections has an infinitesimally small length, which I call DZ. All right? So I have considered my line to be the following. So this line is going to be made out of small sections. All right, and then duplicate this one, duplicate this one, and then here, here, and here, and so forth. So in fact, if you see, I do them like this to help us. If you see, when I connect these two in between with thin wires, I do that only to help me visually because these thin wires do not have any physical length. The only physical length is involved in these ones that I show as thick. And I assume that each one of these, so I have here one very thin section of line, which has a length dz and starts at point A prime, and terminates at point B prime, when the new line starts, also dz, and then terminates at CC prime, and so forth, and then continues until I come to the end of the line, where I connect with the resistance. And you will see why I'm doing that in the beginning of the line, when I connect, where I connect with the voltage. All right. Now, what I can do is I will take, let me see, this one, section. And I will replace this, since it has a capacitance per unit length and an inductance. I will say that my AA prime, I can write it in the following form. Starts at AA prime, and then this is the inductance of the line. So I'm trying to develop a symbolic representation, and this is its capacitance. All right, it looks big, but practically I have done one more thing in this particular representation. I have also eliminated the length of the line, which is dz. But the length of the line is going to come here because this is going to be the inductance per unit length of the line times dz, and the capacitance of the unit length of the line times dz. All right? So a very small section for this transmission line, which means a very small section of this parallel plate with the idle transmission line eventually can be represented, all right, by this circuit, small circuit, where I have eliminated anymore visually the dimension of the line, but I have not ignored it. I have incorporated this small dimension into the value of the inductance, and I have incorporated this small dimension in the value of the capacitance. All right? So why am I doing that? So we're going to see in a second. Because practically, I'm doing it for the following reason. I don't have a way, if I stop here only, if I look at these, then the question is, okay, I know I can apply Ohm's law here. I can apply Kirchhoff's law here, as long as I know these voltage. But then I don't know anything. I don't know how to characterize this line anymore. The only thing that I know is that this line has an intrinsic inductance per unit length and an intrinsic capacitance per unit length. So the only information I have about this line is this one, which I calculated using electrostatics, all right, from what we do. So I know that, but I don't know what is, if the voltage along this point, at this point, say A prime is V, I have no idea how the voltage at the prime is going to be. I don't know how to extract the value of voltage here from this. And Kirchhoff's laws do not apply here the way they apply here. All right, Kirchhoff's laws here, you cannot say, what are you going to say? If you know the voltage here and I want to find the voltage here, how are you going to find it? And there's no way of applying any of those laws unless we transform this into a circuit form. This is a transmission line form. It's not exactly a circuit form, only this is circuit form. Now it is in a circuit form. Now if I use this, I can find the voltage at VB prime if I know the voltage at AA prime. Okay? So how am I going to do that? Let's call this to be V at A prime. Let me extend a little bit this one for a second. I'm going to extend the lines. So I'm going to go here. It does not matter whether I'm extending it, I'm doing it so I can write easier. In circuit form, does not matter how long your wires are, all right? When you design, when you write it. Okay, so I can call this BAA prime. I can call this BBB prime. And you see now that I put two letters, I call this C in this particular, I can call it a different one. Let me call it small b for a moment, or small a. So we don't A prime, okay? Now that's the voltage, and then I'm gonna show you the current. I will not this one. I will call this I will call this B, all right? And therefore, there is gonna be a current here that is gonna go like that. It's gonna be the opposite. And then here is gonna be a current that goes through the capacitor and is called let me put it here, A prime. Now that's a simple circuit theory. And then I'm trying to write my law. So let me start. And of course, voltage VA prime. I'm gonna start. Let me also do this. This is VA prime, okay? Let me do it better. VA prime. All right, so now I'm writing Kirchhoff's laws. What do I have here? That VA prime equals what? Is going to be L D I A dt, and this is times, excuse me, just 1 second. L dz, okay? And then it's gonna be plus B A prime, which in fact is gonna be L dz, write it here, D I A capital A dt, plus how much is the voltage in front through a capacitor in terms of the current is going to be 1 over C dz. Let me see. AC. Well, let me see, A prime dz, and then I will have also on the other side, I will have that V A prime, and I don't know whether I will need that for a moment. Let me keep it there. Is going to be equal to V B prime. And so maybe for that I don't need this, but I will. And then I have also Kirchhoff's current law. I mean that at these points, let me add one more page. And then what else do I have at point A, little a, I have, so this is Kirchhoff's voltage law. K V L. And from KCL, we have that I A equals, the way I have it, A prime plus I A B. All right, so, and then all right. And then I will also call this, let me see one more thing that I will do. I will, because you remember I have these ports, externally, internally you see that. You see the voltages And then you see, in fact, let me also make this voltage red. Internally, you see all of these entities, which are in red. These are internal. Externally, you see this current here at the port, which I call it AA prime. And then you see this current here coming out, which I call A, BB prime. So these are the external, all right? And in fact, so you can see them better, I will give those, make them green. These are the external voltages and current. And it's important to differentiate, all right? So you have internal voltages and currents, and we have external. And the equations, of course, what we want are equations that relate only the external entities. So practically, I will need to write additional equations, which we know that at, we have at A prime. Additionally, we know that A prime equals I capital A lower a, and at B prime, we also have that I B prime equals I lower a capital B. Okay, so now let's see what we are gonna do. One more thing we're gonna do. Now we are gonna assume that we have also a harmonic excitation. We are gonna, as we have assumed from the beginning, we are gonna take into consideration our harmonic excitation. And therefore, we will say here, we know the following, where V A prime equals V naught cosine, or maybe let me write it the following, V A prime cosine omega t. All right, so I will do the same here to be consistent. A prime. All right, since this is a harmonic excitation, what is it that we can do? As we said before, we can replace, all right? We can replace all of the inductors with j omega L and then get rid of the derivatives. We can replace all of the capacitors with 1 over j omega c and get rid of the integrals. And therefore, this equation 1 and 2 can take a much simplified form. So I will have V A prime is gonna be j omega L dz times. And in fact, excuse me for a second, we'll put here the capital because these are the phasor quantities. I capital A plus V A prime and we have that, or in fact here, j omega L dz I A plus 1 over j omega c dz, and then is I A prime, okay? And then we also have that V A prime equals with V B prime. And we have that also from KCL, all right, that I capital A equals I A prime plus IAB, which is, however, IAB is nothing else but IBB prime. So I will write it here, and that's BB prime. So why is this important? Because now I have changed my equations to be all at the port equation. So I'm going to write the following. VAA prime equals J omega L dz IAA prime plus V BB prime. And then I have the current IAA prime to be equal to J omega C dz V B B prime plus I B B prime. That's what I got. All right. So you know why why I wrote? Do you know why I wrote this as this? From the relationship between V and I at the capacitor. All right. So now I have this set of equations. I have two sets of equations that have only the external entities. VAA prime, VBB prime, IAA prime, and IBB prime. And this is very important. Why is that important? Because now I have a relationship between the input voltage and current and the output voltage and current. So for example, if I assume that this is known and this is known, then from here I can find this and this. All right, so practically what that gave me, the whole thing, if you see the whole analysis, gave me two very important equations. We are never gonna do this analysis again. We'll never do it. Oops. Only we'll do it once. You will see, because from this analysis, we are gonna find two parameters which we are gonna use extensively to characterize then the transmission line, and we'll find equations to relate the voltages and currents, and then we will never solve this equation again. So, we'll talk about this a little later. All right, so now you saw here, you'll see something more general. In these are the equations here, which we are going to use when the line does not have any losses. All right, so the line has only an inductance and a capacitance. There are no losses in the dielectric, and there are no losses, and I can write it here, in the conductor. No conductor losses. And no dielectric losses. Now I have to ask you a question. Okay. When I have a dielectric and a material, before I go to dielectrics, any material has three important parameters. All right. It has any dielectric. Let me simplify. Dielectrics, I need to remind you, dielectric materials which are real, but they are good dielectrics, have three parameters: epsilon, mu, and sigma. And if they are good dielectrics, then mu is going to be equal to mu sub naught, all right? And sigma, which is a conduction, shows the conduction of free electrons. It shows a measure of how many free electrons you have. It's going to be small, but cannot be ignored, all right? So it's going to be a small number. But every good dielectric is going to have epsilon, and epsilon, as we know, is going to be epsilon sub r, epsilon sub naught. So epsilon is going to be measured in farads per meter. Nu sub naught is measured in henries per meter, and sigma conductivity is measured in ohms per meter. And why is sigma measured in ohms per meter? Because practically is equivalent to a resistance, all right? So it gives us conductivity here. It's going to give us a conduction current, sigma E, and it tells us it's going to give us a resistive component, which is going to be function of sigma, all right? So it's a measure of the resistance you have in the material, or in fact, it can be a measure of the conductance you're going to have in the material, all right? Conductance or resistance, but it depends on how you want to use it. In materials, we will use that as, let me see, I have to correct myself, because it's ohm minus 1 over ohm, all right? So it's the inverse of ohm. It's ohm minus 1 is conductivity. And you can either see it as measure of a resistance or measure of a conductance, but it's conductivity, and you're going to see it most of the time as in the form of a conductance. So the dielectric materials that you will have in your structure will have an epsilon. So epsilon is responsible for capacitance. We'll have a mu and mu naught, which is going to be inside the inductance. We are going to calculate. And they may have a conductivity. Now, conductivity, which is 1 over ohm per meter in conductance units, I is going to show you how many electrons move through the material, how many free, it's a measure of how many free electrons this material can have. And why is this important? Because if you have free electrons in the material is here. If you have free electrons in the material, not only you're going to have charges here, but you're going to have charges moving through. If you have charges moving through, you're losing charges from up here. So practically, like you have a conductance and you have a current flows. All right? So that's from the dielectric. So if you have losses in the material, then this changes a little bit. This one, I will rewrite, I will copy it. Copy. Paste. So this one, and I will simplify, I'm not going to have the internal anymore because those are gone. We don't need those anymore. But if you have sigma in the material, parallel to C, I'll move C to the other side. Parallel to C, you're going to have a conductance, G. And this G, which is like that, is a function of C, sigma, and it shows what happens if there is a flow of current because there are free electrons in the material, and the free electrons in the material move charges, they move through the material. Okay, create a current through the material. Now, so the value of sigma, which is conductivity in the material, if it's 0, that means that there is no current that flows here. And what of a conductance, which we also saw like this, all right? What value of a conductance G gives 0 current? Resistance. What value of a resistance gives 0 current? It's like open end, all right? It's like gonna be open, which means G is gonna be 0, all right? Do you remember that? A 0 conductance means no current. Why? Because a 0 conductance is 1 over resistance, all right? But usually we show G if it's in parallel. We show G here because C and G have the same kind of units, especially if I put this together. So J omega C, you remember we said it has the units of 1 over R when we did the phasors, 1 over R. Therefore, G has the units 1 over R. And because these both are in parallel, you can sum them up. That's why a lot of times when you see resistances in parallel, you indicate them with a conductance G. Because practically you use the inverse of the resistance, and that allows you to sum this term to this, right? In series, though, a resistance is shown as a resistance. Why? Because in series, resistances are summed up. So it's only for simplification of the formulas, right? So a loss in the dielectric is expressed in terms of this sigma conductance, which is in ohms per unit length, and then creates a conductance that runs across a G, which is proportional to sigma. Okay. Then let's look at the conductors you have. What are the conductors here? These are your metals. All right, let's look at the metal. The metal can be a perfect conductor, which means that all of the free electrons go without any problem. They don't scatter, they don't lose energy, the whole thing, all right? So that's a perfect conductor, no losses in the conductor. If the conductor, as it happens in nature, is not a perfect conductor, nothing is perfect in nature, that implies that there is gonna be a small conductivity, excuse me, it's gonna be a conductivity, not small, let me say that. It's the opposite of a dielectric. A small conductivity in the dielectric for losses, but here is going to be a conductivity, but it's going to be a very large number because in perfect conductors, the conduction is perfect. There is no loss of energy. None of the electrons is losing its energy, which implies that the conductivity is infinite. Infinite conductivity in a conductor implies everything flows, all right? Zero conductivity implies nothing flows. So infinite conductivity, all the electrons go without any problem, any loss of energy. Zero conductivity, nothing goes through, all right? So a perfect conductor has infinite conductivity and a perfect dielectric has zero conductivity. Because nothing should go through. No electrons should flow, free electrons should flow through the dielectric. If they do, you lose energy. But all of the electrons should freely flow in the conductor. If you don't, you lose energy. So practically, why am I saying that? You need to remember. Then the conductivity of a dielectric should be very small. That's why I put it here. You should expect it to be very small. But in a conducting materials, in conductors, metals, for example, what kind of, there is only one, they don't have epsilon and mu. It does not matter if they have anything, it's irrelevant because perfect conductors or very good conductors do not have an electric or magnetic field in there, all right? But they have sigma. And if sigma is not infinite, all right? That implies that the conductor is not perfect. And if it is infinity, it implies that it is perfect. So, no losses here when it is infinity in conductors. And no losses here. Let me put it a little higher. And no losses here when sigma, no losses. When sigma is 0. All right. So I want you to remember that. All right. And if you have losses in conductors, they will show as a series resistance. And here is how they're going to show. So we're going to change that a little bit to make it. Let me see how we're going to change it. All right, move this here. Move this here. Move this one here. And then add the resistance here. So this is the most general form of an infinitesimally small section of a transmission line, where it has a series resistance because of conductor losses and a shunt conductance because of dielectric losses. And if we were to include these losses in these equations, these equations will change into the following form. Oops. Leave it here. Okay. So we'll change this one. And we are going to add practically the resistor here. Here. Plus R dz. And we'll add the conductance here. Plus G dz. And these are then the new expressions for the transmission line of a length dz. Okay, so the last thing I have to do is in fact solve these equations. All right, so we have derived these equations. Here you see the whole thing. And see exactly how we did those. And the next thing that we have to do in these equations is to practically take this here. Okay, what we have to do is to take these equations. Practically, you have seen them in this form, all right? And we do something additional to be able to solve them. We are going to go more in detail to this, but the only thing I want to tell you is because these numbers are multiplied by a DC, I can divide, all right? Practically, I can do the following things. I can assume that my V, B, B prime is nothing else but V, A prime plus its derivative times dz. Why is that? Because I can say from the differential that d v a prime is nothing else but, let me in fact erase this, is nothing else but v, the derivative, the differential rather, is v b b prime minus v a prime. I can say that, that's a differential. And therefore, the derivative of this at that point can be written in this form, all right? And then I can also say that d I a prime, for the same reason, is equal to v to I. And in fact, you can, if it is around there, I will write it rather v a prime v minus v b prime. Okay, let me do it like this. And this is going to be I a prime minus I b b prime dz. So because the dimension is just dz. So practically, if the dimension of the line is only very small, you can say that the voltage here is a different, or the voltage here is going to be this voltage plus a small differential. And the differential is exactly how I write it, dv8. So practically, you can say exactly this, that since the length of the line is very small, my voltage at A at B prime is nothing else but this voltage at A prime plus a differential, right? Voltage. And the same thing we can tell about the current. But this is going to help us rewrite the equations. I will write only these last two things, and then we are going to stop and continue next time. I will rewrite these things. No, excuse me. What did I mean to do? Write it up here. That V, I, B, B prime equals I, A prime plus a small differential. And from these two, we have these expressions. All right, so with this in hand, you can rewrite the following equations. I will cover this below because I want to take you to the two important parameters for the equation, for the line. We are going to do this next time. But I would like you, now that you have that, I would like to familiarize yourselves for next lecture with this, which is nothing else but a rewriting of the previous things in the new way using this. So please, everything that I've done today, because we are going to only do it once. I'm telling you, we are not going to revisit these things because the only reason we are doing them is to find two parameters for the line. And I will tell you right now what those parameters are. A propagation constant, beta, and a characteristic impedance, Z0. The only analysis here is for these two these two parameters, which are extremely important for a line, which is beta and Z0. And we are not going to revisit that. That's why I want you to read it well. So next time, we introduce beta and Z naught, and we start thinking of sections of lines and what we do with transmission lines without any more revisiting that, but only knowing a Z naught and a beta as the two characteristics of a transmission line that have been derived from all of the geometries and all of the material properties, and everything is included there. All right. But we are not going to do this again for every transmission line anymore. Okay. And what I would like you to do is, as I said, you're going to have a quiz, which I am activating right now. Here, let me see. Let me go. Okay, so go here. Here. Okay, we go to quizzes. I'm gonna activate this quiz. Let me see. The quizzes are from review. I will do this too. They're all review, as a matter of fact. So one is to find frequency and wavelength. The other is to find the phasor forms. Remember the phasors? Okay. So I will activate both of those. Homework. And activate homework. Okay. So for Monday. Okay. Thank you. Thank you. Yes.
When you wrote should the capacitor voltage be this in terms of DT?
Yes. Oh no. This. Yes. Excuse me. That should be in terms of DT, like here.
Okay.
I put this wrong. Thank you. Thank you for showing me. I will correct it.
Okay. Writing. We had for the conductivity, the sigma with the two less than sounds.
Yes.
Does that mean it's very small? Just
yes.
That. And then I want to let you know that next Friday I will not be in class.
Okay.
That's rain day, and I don't think that's a university excused absence. But I was going to call and check with.
What day is that?
Friday the 8th.
Yes. What do we call it?
Ring day. So I'm getting my ID ring.
Ah, ring day. Okay, I'm sorry.
Yeah, you're okay.
Nice.
I just wanted to let you know.
So you have a whole thing celebration.
Yeah.
Nice.
So it's, my time slot is